All right, so this video is going to focus on energy changes associated with electrons getting excited and moving from a lower energy level to a higher energy level, and then emitting that energy and returning back from that excited energy level to one of less energy. The atomic spectrum of hydrogen is going to be our focus. This is going to be applicable to Bohr's model of the atom. And what we see here is that with your continuous spectrum, and you would see all of the possible wavelengths within that visible spectrum. That's when you see your rainbows. Line spectrums are only going to show certain colors of light, certain lines, and it's going to depend on what you're working with, whether it be hydrogen or other elements or even smaller compounds. These are known as discrete spectrums, and these lines that we see, these emission lines, are only showing us the wavelengths of light that are emitted by hydrogen when its electrons get excited and then return back. We do not see all of the continuous spectrum because only certain energies are available for the electron that hydrogen has. So the Bohr's model, again, is going to be applicable only to hydrogen. It did not work for larger atoms. And this is the idea that the electrons are moving in a planetary motion. They're moving in circular orbits. And so we can calculate the energy associated with the energy levels in which that electron can move using this equation. E equals negative 2.178 times 10 to the negative 18th joules. And then that would be multiplied by z squared divided by n squared. So E is going to represent the amount of energy that would be needed to move that would be present per energy level. Z is the charge of the nucleus. So for hydrogen, that would be 1. So 1 squared would still be 1. And then N is going to be one of your energy levels. N of 1 up to, right now we know of up to N of 7. And those correspond to your rows on the periodic table. And if you wanted to determine how much energy was going to need to be transferred to move from one energy level to another, you could calculate delta E by taking the difference between your between your final state that your electron was placed and its initial state. And so here we see a Bohr model representing the 5 energy levels so far. And then you can see different wavelengths of light being emitted, whether it be 4 to 2, 3 to 2, or 5 to 2, 3 to 2, or 4 to 2. And they each are going to correspond with specific wavelengths of light associated with those transitions. So we're going to calculate the wavelength of light that would be emitted when hydrogen is going to have its electron move from an energy level of 5 to an energy level of 3. And then we'll show those show that transition on an energy level diagram. So I showed you that equation for energy per energy level. And if you wanted to calculate it for a transition between energy levels, you could put that equation together and you would pull out your constant and get negative 2.178 times 10 to the negative 18th joules. Remember, this is for hydrogen, so your numerator will be 1 squared, which would just be 1. And then you would divide it by n final squared minus 1 over n initial squared, your energy levels. Well, we started at 5, an energy level 5, and we went to an energy level of 3. So it would be 1 over 3 squared minus 1 over 5 squared. At this point, you can do it in your calculator, and you're going to get that your energy level will be, or the energy transition will be 1.55 times 10 to the negative 19th joules. And light was being emitted. You were moving from a higher energy level to a lower energy level. So energy would need to be released which is why delta E was negative. This is an exothermic change. So if I was going to show this with, oh sorry, we're not quite done yet. We wanted to calculate the wavelength of light. So we were able to use this relationship between the energy levels to calculate delta E. And we can use delta E to help us find wavelength because wavelength is proportional to energy. So if we use that equation from our first part of this unit, Hc over delta E, we now know the energy requirement that would be needed for that wavelength of light to be emitted. And yes, we know it's an exothermic change, but wavelengths are only going to be positive values. So we can just take the absolute value of that energy transfer, 1.55 times 10 to the negative 19th joules. The joules cancel, the seconds cancel, and when we do our math through, we get that our wavelength is 1.283 times 10 to the negative 6th meters, or around 1283 nanometers. So this would be outside of your visible spectrum, because again, your visible spectrum is going to fall between 400 and 700 nanometers. So if I was going to show this with the energy level diagram, the transition, the electron that is being emitted would be moving from an N of 5 to an N of 3. You'll notice that each of the N levels has a different amount of space between it and the next energy level. The biggest jump is obviously between 1 and 2, but then you'll notice as you keep getting up, those differences become smaller and smaller. So I believe this is our last question. Here we have an excited hydrogen atom emits light with a frequency of 1.141 times 10 to the 14th hertz. So remember, we can use our frequency to help us find wavelength. We can also use frequency to help us find energy. We want to, it says this was needed to reach the energy level for N of 4. And it's emitting light, so it's releasing energy to be able to get to an N of 4. And what principal quantum level did our electron begin? So if we're wanting to know what energy level we started at, and we know that we ended with an N of 4, we need to figure out how much energy was being transferred to allow this change to occur. So we're going to use our frequency to help us find that energy transfer by multiplying it by the Planck's constant. And when we do that, we get that the amount of energy that was emitted was 7.560 times 10 to the negative 20th joules. The only time the sign for delta E truly matters is when you're wanting to calculate anything related to those energy levels, when you're either needing to add quantums of energy to move from a lower to a higher energy level, or whether you are emitting light or emitting energy to be able to move from a higher energy level to a lower one. So with that in mind, when we want to calculate that principal quantum level, we're going to need to use the fact that this was an exothermic change to be able to relate our transition between levels. We know we ended with a level of 4, so we would put that in for our N final, and we would want to solve for N initial. At this point, you can graphically use your calculators to determine what N initial is, but these N levels are always going to be pretty close to whole numbers. And if you go through and do the math, or if you graph it on your calculator, you're going to get that this electron must have started in an energy level of around 6.